Welcome to The Sleepy Scholar. It's lovely to have you. Before we begin, I'd love to know where you're watching from tonight. A quiet bedroom, a sleepy train ride, a cozy couch. Wherever you are, I hope you're comfortable and ready to gently drift into thought. If you enjoy these relaxing explorations, a like and subscribe really helps this sleepy channel. And to those already subscribed, thank you. Your support means more than you know. I'll try not to make tonight's topic so interesting it keeps you wide awake. But if it does, at least you'll better understand why particles act like waves and why reality seems to hesitate until someone's watching. A small price for a restless night. So, let's begin. What is quantum physics? And why does it so often sound like the universe is making things up? The world we see and touch feels solid and predictable. If you drop a teacup, it falls. A coin lands. The moon does not vanish when you close your eyes. But in the early 20th century, scientists looked much closer. The deeper they peered, the stranger things became. Light, they found, could act as both a wave and a particle. Particles could exist in many places at once until measured. And observing something didn't just reveal what was there, it seemed to change it. This wasn't bad data. It was real, reproducible, and it shattered the laws of classical physics. Quantum physics was a new way of seeing reality, a strange one where certainty is replaced by probability. We'll drift gently through that world. There's no need to grasp every equation. We'll move slowly, one mystery at a time, from the earliest puzzles to the modern questions that still keep physicists up at night. So, tuck yourself in, close your eyes, and let's explore a world where emptiness isn't empty, and where everything you thought you knew is only probably true. At the turn of the 20th century, physics felt almost complete. Laws were understood. Thermodynamics was tidy. Some believed all big questions were answered, with only a few odd bits left. One of those involved what happens when you heat an object. When you warm metal, it glows red, then orange, then white. This black body radiation comes from emitting electromagnetic radiation. It seemed easy to explain, but the math refused to cooperate. Classical physics predicted something bizarre. As temperature increased, it should emit more energy at shorter wavelengths. This led to infinite energy at high frequencies, a scenario nicknamed the ultraviolet catastrophe. No tweaking of classical equations could stop the math from spiraling into nonsense. Reality didn't match the predictions. Enter Max Planck. In 1899, Planck, a careful German physicist, did something quietly revolutionary. To fix the math, he introduced a strange idea. What if energy couldn't be emitted in any amount, but came in tiny, indivisible packets like coins you can't split? He called these packets quanta. This was a shift from the continuous view of energy. Instead of a smooth flow, energy would arrive in steps depending on the radiation's frequency. Planck introduced a constant to describe the size of these packets. When he plugged this into his equations, the infinite energy problem vanished. The equations worked. They matched the real world. Planck had solved the ultraviolet catastrophe. And yet, he didn't quite believe it. Planck described his solution as a mathematical trick, a way to make the numbers behave, not how the universe actually worked. He assumed future physicists would find a better explanation. Quantization was a temporary patch to him, not a fundamental truth. He couldn't have known his trick would become the cornerstone of a new way of thinking. His idea of discrete energy packets laid the groundwork for quantum theory. At the time, it felt like a side note, not a revolution. Planck just wanted the math to work. Yet, by introducing quantization, he had lit the first match. This humble beginning in a quiet 1900 paper didn't shout its importance. From that point, physics would never feel finished again. By the early 1900s, light was thought to be well understood. Maxwell's equations had shown that light behaved like a wave. It bent, bounced, and interfered. After Planck's introduction of quanta, most physicists assumed things would settle down. But then came a riddle involving metal, light, and a surprising refusal to cooperate. It was called the photoelectric effect. If you shine light on a metal surface, electrons can be ejected. Light delivers energy. Energy kicks out electrons. According to wave theory, increasing the light's brightness should increase the energy transferred. A brighter wave should shake electrons loose more effectively. But that's not what happened. Scientists found something strange. Shining brighter light didn't eject electrons with more energy. What mattered was the light's frequency. If the light was below a certain frequency, even a very bright light did nothing. No electrons were ejected. But above that frequency, even a dim beam could knock electrons free. The threshold was sharp and made no sense under wave theory. Enter Albert Einstein. In 1905, his miracle year, he published a paper that changed everything. He proposed something bold. What if light wasn't just a wave? What if it behaved like a particle, a tiny bundle of energy? Einstein suggested light was made of individual packets of energy, later known as photons. Each photon carried energy determined by its frequency. If a photon had enough energy, it could knock an electron loose. If it didn't, no amount of photons could do the job. Einstein's idea built on Planck's work, but went further. He wasn't just using energy packets as a mathematical trick, he was suggesting light itself was made of these packets as a literal description. It was a revolutionary claim. Many physicists clung to the wave model. After all, light clearly showed wave-like behavior, like creating interference patterns. If light was particles, how could it also be a wave? Einstein didn't deny the wave nature. He proposed something stranger. Light was both a wave and a particle. It could act like one or the other depending on how you observed it. This duality wasn't a trick, it was fundamental to light itself. Imagine sunlight filtering through a window. It spreads like a wave. But zoom in and you'd find tiny quanta of energy knocking into atoms. This idea of wave-particle duality is one of the strangest in physics, challenging the very categories we use to describe reality. Einstein's photon explanation matched the experimental results beautifully. The energy of each photon depended on its frequency, just as Planck suggested. It neatly explained why low-frequency light couldn't eject electrons. The individual photons lacked the punch. In 1921, Einstein received the Nobel Prize not for relativity, but for his explanation of the photoelectric effect. Still, even Einstein found the quantum world uncomfortable. He resisted the probabilistic interpretations, famously declaring that God does not play dice with the universe. But the rules were changing. Light refused to fit in a tidy box. It came in quanta, danced as a wave, and collided like a particle. What began as a simple experiment with light and metal ended up shaking the foundations of physics. Imagine a simple setup, a flashlight, a piece of cardboard with two tiny slits, and a screen. In this humble arrangement, we find one of the most mind-bending experiments. In classical physics, waves and particles behave differently. A wave, like water, spreads out and interferes with itself, creating a pattern of peaks and troughs. Particles, like tiny rubber balls, would just create two clusters of impacts. So, what happens with light? When scientists first shined light through two slits, it behaved like a wave. It spread out and formed an interference pattern, a series of bright and dark bands. So far, so good. But then things got weird. Using sensitive equipment, researchers fired just one photon at a time. You'd expect these lone photons to act like particles, gradually forming two bright spots. That's not what happened. Even one at a time, the photons built up the same interference pattern as before. How could a single photon interfere with itself? Did it go through both slits at once? The pattern persisted, suggesting each photon traveled through both slits simultaneously. If that wasn't strange enough, physicists decided to peek. They placed detectors at the slits to observe which path the photon took. But when they looked, the interference pattern vanished. As soon as the photons were observed, they stopped behaving like waves and acted like ordinary particles. No more interference. It was as if observing forced the photon to make a decision. Turn off the detectors, the interference returned. Turn them on, it vanished. The implications were staggering. It wasn't that the devices disturbed the photons, these were non-intrusive. The issue wasn't how we observed, but that we observed. The mere potential to know the path was enough to collapse its wave-like behavior. Reality, it seemed, cared if it was being watched. This experiment has been repeated countless times, even with large molecules. The result is the same. Unobserved, they act like waves. Observed, they behave like particles. This sits at the heart of quantum physics. It suggests particles don't follow strict paths. They exist as a spread of possibilities. Only when a measurement is made does that cloud collapse into something definite. Some prefer probability language. Others, in the many worlds camp, imagine each possibility branching into a new universe. But the facts remain until observed. The particle doesn't commit. This simple test turned into a profound mystery about reality itself. Is reality fundamentally uncertain until we ask it to reveal itself? The universe at its core is not a clockwork machine. It's a shimmering tapestry of possibilities responding in curious ways to our gaze. In quantum physics, one piece of math whispers through the theory, Schrödinger's equation. Don't worry, this isn't a math lecture. This equation is the quiet heartbeat of the quantum world. In the 1920s, physicists were wrestling with how to describe particles that acted like waves. In 1926, Schrödinger proposed an equation describing how their wave functions evolved over time. It was elegant and shockingly effective. The key concept is the wave function, often shown as the Greek letter psi. Think of it as a mathematical whisper telling us everything we can know about a quantum system, where a particle might be, its likelihood of being there, and how it might be moving. The wave function gives probabilities, not hard answers. Classical physics draws a neat arrow for a particle's position. Schrödinger's world offers a hazy, rippling cloud, a wave of possibilities. This is where the magic happens. Schrödinger's equation lets us evolve this cloud over time, showing how the possibilities shift. And when we measure the particle, ask where are you? That wave function collapses. The cloud disappears and we get a single, definite answer. But only after we've looked. This wave-based view is profoundly different from the mechanical picture. Instead of particles on predictable paths, we see swirling fields of probability full of uncertainty until observation pins them down. Imagine you're blindfolded in a room with a quiet cat. You toss little balls and listen for where they land, building a mental map of where the cat might be. That map is like the wave function. It's not a picture of reality as it is, but as it might be. An equation telling you how that map changes is what Schrödinger did for electrons. The actual equation is continuous, allowing these probability waves to ripple like water. It respects nature's symmetries, like energy conservation. But it doesn't care for certainty. It tells us what could happen, not what will. And it works beautifully. Physicists have used it to describe everything from atomic structure to molecular bonds, semiconductors, and superconductors. It even predicts quantum tunneling, where particles slip through barriers they shouldn't cross. One of its most famous successes was explaining the hydrogen atom. Before quantum mechanics, no one could explain why electrons settle into specific orbits. Schrödinger's equation revealed electrons aren't miniature planets. They form standing waves, stable patterns of probability around the nucleus. These are the orbitals, the soft clouds in textbooks. They represent the real, measurable likelihood of where an electron might be found. They exist because the electron isn't a simple particle, it's a ripple in a sea of probabilities. It's strange, but beautifully consistent. Schrödinger's equation has aged like fine wine, predicting the behavior of the very small with astonishing accuracy. Yet it remains abstract. You can't hold a wave function, but it's there, describing the ghostly potential of everything. And then there's the philosophical side. What is a wave function? Is it our knowledge, or is it an actual part of reality until it collapses? Different interpretations argue fiercely, but the equation itself doesn't take sides. Even Schrödinger had mixed feelings. He disliked the idea that particles lacked definite properties until observed. His famous thought experiment of a cat, simultaneously alive and dead, was meant as a critique of the uncertainty his work unleashed. Still, it's hard not to admire what he built. In a world demanding yes or no, Schrödinger offered a shimmer of maybe. His equation doesn't shout, it suggests, revealing a universe quieter, subtler, and more mysterious than we ever imagined. In the classical world, you can know where something is and how fast it's going at the same time. A radar gun clocks a car's speed while GPS tells you its location. No mystery. But the quantum world doesn't play by those rules. In the 1920s, Werner Heisenberg introduced the uncertainty principle, stating that at the most fundamental level, there are limits to what we can know. Specifically, the more precisely we know a particle's position, the less precisely we can know its momentum, mass times velocity, and vice versa. In everyday terms, this sounds silly. How could knowing where a train is make you unsure of its speed? But at the quantum scale, reality doesn't allow that clarity. This isn't about our measuring tools being clumsy. The uncertainty isn't in our instruments, it's woven into the fabric of the universe itself. Let's say you try to observe an electron. To do that, you might shine light on it. But light is made of photons, and photons carry energy. When one hits the electron, it changes the electron's motion. It's like finding a soap bubble by throwing tennis balls at it. You'll find it, but you'll destroy it. Still, Heisenberg's point wasn't just about disturbing particles. His principle is built into the mathematics. Even if you could observe without interfering, the uncertainty would remain. At the heart of the uncertainty principle is the wave nature of particles. A particle like an electron is described by a wave function, a spread-out cloud of possibilities. If the wave is wide and smooth, you can't tell where the particle is exactly, but you can estimate its momentum. If you narrow the wave to pinpoint the position, the momentum becomes more uncertain. It's a cosmic trade-off. The product of the uncertainties is always greater than or equal to a tiny number derived from Planck's constant. That number is very small, so in our world, the effect is negligible. But at the scale of electrons and atoms, the uncertainty is impossible to ignore. It shapes the behavior of the world beneath our senses. If you try to trap a particle in a very small space, it starts to behave wildly. Its momentum becomes highly uncertain. Try to pin it down further, and it resists more. Nature doesn't like being told exactly where things are. One way to think about it is like trying to hold mist. The tighter you squeeze, the less you have. This principle is a philosophical warning label. It tells us knowledge has boundaries, not due to human limitations, but because of how reality is built. We're dealing with possibilities and waves that refuse to be nailed down. This principle also explains why atoms don't collapse. You might wonder why electrons don't just fall into the nucleus. Thanks to the uncertainty principle, electrons can't sit still. If an electron fell into the nucleus, its position would be perfectly known, meaning its momentum would become infinitely uncertain. That requires infinite energy. Nature says no. So, electrons hover because quantum rules won't allow anything else. The principle creates a built-in resistance to absolute confinement. This strange limit also applies to measurements of energy and time. Increasing precision in one means surrendering certainty in the other. Yet, there's something comforting here. Uncertainty isn't chaos, it's a structured ambiguity, a graceful fuzziness. It gives the universe its texture. It allows particles to tunnel and atoms to be stable. Without it, reality might be too rigid for life. Heisenberg showed that some aspects of nature will always remain out of reach. That's not a failure, it's just how things are. The uncertainty principle invites us to make peace with not knowing, to appreciate the softness beneath the surface. It's a reminder that the deepest truths are not always sharp-edged, but cloudy, rippling, and unresolved. In our experience, things are in one state. A coin is heads or tails, a switch on or off. In the quantum world, this tidy division breaks down. Objects at the smallest scales can hover in a strange in-between, a blend of all possible outcomes. This is quantum superposition. Imagine flipping a coin. In the classical world, it's heads or tails the whole time, just hidden from you. Quantum systems don't work that way. A quantum coin enters a state of superposition, a weighted combination of both heads and tails at once. It isn't undecided, it is genuinely, physically in both states until you observe it. When you check, the superposition collapses. The coin chooses a face and your measurement becomes real. But before you looked, it wasn't just unknown, it was both. Superposition was first introduced to describe quantum particles like electrons, which exist as wave functions, mathematical expressions of probabilities. All possibilities coexist until a measurement selects one. You can picture it as a foggy landscape of outcomes. The particle is spread across every possible route. When you interact with it, the fog snaps into a single location. This led to one of the most famous thought experiments, Schrödinger's cat. Suppose you place a cat in a sealed box with a radioactive atom, a detector, and poison. If the atom decays, the detector breaks the vial and the cat dies. If it doesn't, the cat lives. Quantum mechanics tells us that until the atom is observed, it's in a superposition of decayed and not decayed states. By extension, the cat is both alive and dead until someone opens the box. This wasn't meant literally. Schrödinger was highlighting the absurdity of applying quantum rules to large objects. But the idea struck a chord, painting superposition as something with deeply strange implications for reality. Yet superposition is not a flaw. It's one of the most powerful features of quantum mechanics. Modern quantum technology depends on it. A classical computer uses bits, which are either 0 or 1. Quantum computers use qubits. A qubit can exist in a superposition of both 0 and 1 at the same time. This means a single qubit holds more information. When multiple qubits are entangled, they can represent a vast number of states simultaneously, allowing quantum computers to perform certain calculations like simulating molecules far more efficiently. Superposition also appears in quantum cryptography and quantum sensing. These are real technologies, but superposition is delicate. The slightest interaction with the environment, stray photons, vibrations, can collapse the wave function. This process, decoherence, is one of the biggest challenges in building stable quantum systems. It's like balancing a feather on a pencil tip while someone sneezes nearby. That fragility is part of what makes quantum systems fascinating. They offer power, but only under precise, isolated conditions. This leads to a deeper question. Is the wave function reality or just our knowledge? Some interpretations suggest it represents our best guess. Others say the wave function is physically real, the particle truly is in multiple states. Either way, quantum superposition invites us to loosen our grip on classical logic. It tells us opposites can coexist, this and that, here and there, all at once. Reality at its core is not a single thread, but a tapestry of possibilities, overlapping and unresolved until observation pulls one strand loose. It's strange, but it's also beautiful. In this rule, we find a universe that isn't rigid, but flexible, not mechanical, but poetic. Imagine you have two gloves, a left and a right. You put each in a box and send one to the other side of the world. You don't know which is which. The moment you open one and see a left-handed glove, you instantly know the other is right-handed. This isn't mysterious, it's logic. The gloves were always one left, one right. Quantum entanglement isn't like that. Entangled particles are more like gloves that don't decide which hand they are until after you open one box. Whichever one you open first instantly tells the other how to behave, no matter how far apart. It's not just that the outcome is correlated, the properties don't seem to exist until you measure one. Measuring one instantly affects the other. This is quantum entanglement, one of the strangest features of the quantum world. When two particles interact, they can become entangled, their quantum states linked. Whatever happens to one affects the other, even when separated by great distances. Imagine two entangled photons. They stay in a shared quantum state, a superposition. Only when you measure one does the outcome become definite. At that exact moment, the other state also becomes definite, instantly. No signal, no delay. If you measure one photon in Paris, the other in Tokyo responds at that very moment. This is what Einstein famously called spooky action at a distance. Einstein believed firmly in locality, the idea that processes at one location can't instantly affect things far away. Nothing, not even information, travels faster than light. The idea of two particles coordinating outcomes instantaneously made him uncomfortable. In 1935, Einstein and his colleagues published a paper challenging quantum mechanics. They argued it must be missing something, some hidden variables determining the outcomes all along. Decades later, experiments confirmed entanglement is real. Those hidden variables never showed up. In the 1960s, John Bell devised a test, Bell's theorem, to distinguish between quantum predictions and hidden variable theories. When physicists perform these experiments, quantum mechanics wins. Entangled particles behave in ways that can't be explained by local hidden variables. The results are random yet perfectly correlated. It's as if they share a private script, unwritten until the curtain rises. Still, this doesn't mean you can use entanglement to send messages faster than light. That would break causality. While particles react instantly, the outcomes are fundamentally random. You can't control what result you get, so you can't encode information. The instant connection is real, but it can't be used for communication. It's like two people flipping coins. Each result is random, but when one flips heads, the other always flips tails. They aren't sending messages, they're just in sync in a way that defies space. This connection doesn't weaken with distance. Physicists have entangled particles over hundreds of kilometers using satellites. But what is entanglement? A shared identity? A subtle form of information? No one is completely sure. Some see it as evidence of a deep, non-local fabric to reality. Some researchers propose that space-time itself might emerge from networks of entanglement. If true, entanglement isn't something that happens in space, it's what holds space together. Entanglement has practical applications. It's the foundation for quantum teleportation, the transfer of quantum states, not people. it underlies quantum key distribution, a method of secure communication. In quantum computing, entanglement allows for complex operations, giving these computers their power. This spooky action is now a cornerstone of cutting-edge technology. Entanglement reminds us that the universe is not a collection of independent objects, it's a deeply interconnected web where separateness is sometimes an illusion. At the tiniest levels, this silent partnership is humming away everywhere all the time. There are few animals in science more famous than Schrödinger's cat. This feline has become the mascot of quantum physics, a creature in a thought experiment so peculiar it's often mistaken for satire. And in a way, it is. The story begins in the 1930s, when physicists were grappling with what quantum theory meant. The math worked, but what was it saying? Was the wave function real? Did particles exist in multiple states until measured? Erwin Schrödinger, already famous for his equation, was skeptical of how far some pushed the idea of superposition. In his view, applying the rules of electrons to everyday objects, like a cat, was fishy. So he posed a dark, playful question. Imagine a sealed box containing a cat, a tiny radioactive atom, a detector, and a vial of poison. If the atom decays, a random quantum event, the detector detects it, the trigger breaks the vial, poison is released, and the cat dies. But here's the twist. Quantum theory says until we observe the atom, it exists in a superposition of both decayed and not decayed states. This means the entire system, the detector, the poison, and the cat should also be in a superposition. The cat is both alive and dead, literally, according to some interpretations. Of course, no one put a cat in a quantum box. Schrödinger was making a point. He found it absurd that a cat could exist in such a blurry, undefined state. It was nonsense. Yet the idea stuck, capturing the essence of quantum indeterminacy, a cat that is both dead and alive until the box is opened. It's about possibility. Until observation collapses the wave function, the system contains every outcome simultaneously. Schrödinger's cat isn't about cats, it's about what we're allowed to say about the world before we've looked. In quantum mechanics, observation is central. Before you measure, a system is a cloud of probabilities. The moment you interact with it, the cloud collapses. The system picks a state. One possibility becomes real, all others vanish. But what counts as a measurement? A conscious observer? A mechanical detector? An interaction with the environment? Different interpretations give different answers. Quantum theory, while successful, is oddly silent about what's really happening in between. The Copenhagen interpretation essentially says, don't worry about it. The wave function tells us everything we can know. Others prefer the many worlds view, where the cat is both alive and dead in separate branching universes. Opening the box just selects your path. There's also the decoherence approach, arguing that interaction with the environment filters out superpositions, making the system appear classical. All agree, quantum systems don't behave like classical objects, they evolve probabilistically. So, the box is a boundary between the quantum and classical worlds where questions like, is the cat alive, don't have simple answers. We must say the cat is in a superposition until we open the box and collapse that ambiguity. The cat is a macroscopic way of expressing that an electron, too, explores all possible paths at once until observed. The difference is scale, not principle. And that's what troubled Schrödinger. If the theory applies to everything, then at some level we are all part of a superposition. What collapses our wave function? Where does the observer line stop? In the end, Schrödinger's cat isn't just about life and death, it's about knowledge and the strange dance between reality and observation. It's about what it means to say something, when the act of saying so might change the outcome. It's a reminder that in the quantum world, certainty is rare, and sometimes the universe waits for us to peek inside. In the everyday world, walls are straightforward. If you throw a tennis ball at a wall, it bounces off. Simple. But in the quantum world, predictability takes a holiday. A particle can hit a wall, not have enough energy to pass through, and yet still show up on the other side. No smashing, no squeezing, it simply appears. This phenomenon is called quantum tunneling. It's real, measurable, and fundamental. And it all comes down to probability. In quantum mechanics, particles are described by wave functions representing a spread of possible positions. These waves can extend across space, fading gradually. Even if there's a region the particle technically shouldn't reach, the wave function might still stretch into that forbidden zone, albeit faintly. Imagine a particle approaching a barrier. In classical physics, this is a hard stop. But the quantum wave function doesn't vanish. It tapers off like a whisper fading through a wall. If the wall isn't too wide, that whisper can make it to the other side. The particle might not have enough energy to climb the barrier, but its wave function can tunnel through. If part of the wave function makes it, there's a small but non-zero probability the particle will show up there. This has concrete consequences. Take radioactive decay. Some atomic nuclei are unstable, ejecting alpha particles. These particles are trapped by a powerful nuclear barrier. Classically, they don't have enough energy to escape, but they do escape. Quantum tunneling is the reason. Inside the nucleus, the particle's wave function stretches. There's always a chance it will tunnel through. Over time, that small probability adds up and the particle pops out. Tunneling is also critical for nuclear fusion, the energy source of stars. In stars, hydrogen nuclei are crushed together. But even at extreme conditions, they don't have enough energy to overcome the electrostatic repulsion between them. Yet stars shine. Tunneling explains why. At high temperatures, nuclei get close enough for their wave functions to overlap. There's a tiny chance one will tunnel through the barrier and fuse. Multiply that by the unthinkable number of particles in a star, and you get a brilliant fusion process. We use tunneling on Earth. The Scanning Tunneling Microscope, STM, visualizes individual atoms. It brings a sharp tip extremely close to a surface. At that distance, electrons can tunnel between the tip and the surface. By measuring this current, the microscope builds a detailed map. The STM doesn't touch the atoms. It relies on electrons slipping quietly through empty space. Tunneling is also at the heart of some electronics and is a factor in the future of computing. As transistors shrink, electrons can tunnel through barriers they shouldn't. This creates challenges but also opens the door to new quantum technologies. At its core, tunneling teaches us something profound. We often think of hard boundaries. But the quantum world is nuanced. Barriers are not impenetrable, they are probabilistic. They are suggestions, not absolutes. Because of tunneling, particles aren't confined to straight paths. They can cheat, slip, blur through the cracks of logic. They remind us the universe is not a machine, but a shimmering tapestry of possibilities. The tennis ball still bounces, but the electron might just glance at the wall and say, "I'll take the shortcut," and nature lets it. In everyday life, we think of nothing as empty. We often picture the vacuum of space as a perfect silent void. But in quantum physics, nothing is never really empty. The quantum vacuum is a restless, jittering stage. It's not filled with atoms, but it's far from blank. Even when all particles are removed, the vacuum still seethes with energy. At the smallest scales, space is alive with invisible activity, particles flickering in and out of existence. It's like the hum beneath silence. It all starts with uncertainty. Heisenberg's uncertainty principle also applies to energy and time. This means that even in a region where energy should be zero, it can briefly fluctuate. These fluctuations give rise to virtual particles, which appear spontaneously, exist for a fleeting moment, and then vanish. They're called virtual, not because they're imaginary, but because they can't be directly observed, only inferred. These quantum blips have real consequences. One striking example is the Casimir effect. Imagine placing two thin, perfectly conducting metal plates extremely close together in a vacuum. Classical physics says nothing should happen. Quantum mechanics says otherwise. Because the space is so small, only certain wavelengths of virtual particles can exist there. Outside the plates, there's no such restriction. The result, slightly more pressure from virtual particles outside the plates than between them. This imbalance creates a force pushing the plates together. This tiny force has been measured, proving that even nothing has a kind of substance. This vacuum energy isn't just in labs. In cosmology, the energy of empty space, which we call dark energy, might be responsible for the accelerating expansion of the universe. But there's a catch. The predicted energy of the quantum vacuum is enormous, wildly larger than what we actually observe. This is often called the worst prediction in physics, and no one has fixed it. At the quantum scale, virtual particles play a role in other phenomena. In quantum electrodynamics, the interaction between charged particles is mediated by the exchange of virtual photons. Even the mass of protons is affected by the swarm of virtual quarks and gluons flickering inside. Stable matter is the result of interactions with this invisible, fluctuating vacuum. While these particles appear and disappear, their influence is everywhere. They slightly alter the energy levels of electrons. They're woven into every interaction. This has been tested. When we correct calculations to include vacuum fluctuations, like in the Lamb shift, the predictions match reality with breathtaking accuracy. The math is weird, but the results are solid. The quantum vacuum is the most fundamental field. All other fields exist within it. Some physicists suspect the vacuum holds clues to deeper truths, like quantum gravity or space-time itself. The vacuum is not a passive backdrop, it's active, structured, and full of potential. Even in the coldest regions of space, the quantum vacuum is there, vibrating, whispering the rules of existence. It's humbling to think that nothing is never truly nothing. In the gaps between particles, something is always happening. In the quantum world, reality doesn't behave like a story with a clear beginning, middle, and end. Particles drift in clouds of probability. They superpose, entangle, and tunnel. But the most mysterious twist comes when we ask, what happens when we look? This simple act of observing, of measuring, seems to trigger a dramatic shift, wave function, collapse. Before measurement, a particle is described by its wave function, a mathematical object holding all possible outcomes. The electron isn't in one place, it's in a blend of many. Its spin isn't up or down, it's both. The wave function is a shimmering fog. But then you measure it, you ask, where is it? In that instant, the wave function collapses, the fog condenses. All possibilities snap into a single reality. The electron is suddenly there. This collapse is abrupt. One moment the system is in superposition, the next, it's locked into a definite state. That's weird enough, but no one knows what causes the collapse. Is it the physical interaction? The transfer of information, consciousness? The collapse of the wave function, though central to quantum theory, is not well understood. It might be the biggest mystery in modern physics. Different interpretations try to answer this. The traditional Copenhagen interpretation says the wave function isn't a real object, just a tool for predicting probabilities. Collapse happens when we gain information. Before that, asking what's really happening isn't meaningful. The electron isn't anywheres until we look. This is practical, but it leaves many unsatisfied. Then there's the many worlds interpretation, which throws collapse out entirely. The wave function never collapses. Instead, every possible outcome happens, just not in your universe. Measure an electron's spin and the universe splits. In one version, it's spin up, in another spin down. You only experience one, but the others still exist in parallel. No collapse, just branching realities. It's consistent with the math, but it comes at the cost of multiplying universes. Other interpretations aim to make collapse real. Objective collapse theories suggest the wave function is a physical thing that collapses spontaneously, and measurement just increases the chance. Then there's cubism, suggesting the wave function describes our beliefs collapse isn't a physical event, but a mental update. There's also decoherence, which helps describe how superpositions seem to vanish in large systems. When a quantum system interacts with its environment, it becomes entangled with it. That entanglement causes the interference patterns to disappear. To us, the system looks like it collapsed. Decoherence explains why cats don't stay both alive and dead, but it stops short of saying how one outcome becomes real. So we sit, more than a century later, with wave function collapse as a ghost in the machine. The math works, but what collapses? When? Why? Is it even real? Some researchers believe we need a new theory. Others are content with the ambiguity, saying the predictions work and the rest is philosophy. But philosophy matters here. The question is about what the universe is. Is reality probabilistic? Is it observer-dependent? Is it constantly branching? You can think of collapse as the moment the quantum world tips into the classical, like water freezing. But we don't know the rules. We just know that at some point the fog becomes a shape and possibility becomes presence. Maybe the universe is content being undecided. Maybe we're the ones who insist on conclusions. If quantum physics had a hometown, it would be Copenhagen. Not for the scenery, but because it's where some of the strangest ideas in physics were first seriously discussed and accepted. At the heart of this is Niels Bohr, a Danish physicist who helped shape the Copenhagen interpretation. The idea is deceptively simple. Quantum systems don't have definite properties until they're measured. An electron doesn't have a fixed position. A particle doesn't choose a state until an observation forces it to. Before measurement, reality is a fuzzy cloud of possibilities. Measurement doesn't just reveal something, it creates the outcome. Reality isn't quite real until we ask it to be. Bohr and his colleagues weren't trying to be mysterious, they were trying to make sense of experimental results. When they treated particles as probability waves that resolve upon measurement, things clicked. The wave function, in this view, isn't physical. It doesn't describe a particle's actual position. It encodes everything we can know about the system, a catalogue of possibilities. This leads to a central claim. Questions about a system's state before measurement are meaningless. Asking where the electron was doesn't make sense because where only becomes meaningful after the measurement. Reality snaps into focus the moment you look. The particle didn't have a true nature yet. Understandably, not everyone found this satisfying. Albert Einstein was uneasy. He wanted a universe that existed independently of observation. He believed in an underlying objective reality. To Einstein, this sounded like saying, "The moon doesn't exist unless you're looking at it." Bohr embraced a pragmatic ambiguity. His position was that quantum theory tells us what we can say about nature, not what nature says. The role of science isn't to discover what's really out there, but to describe experimental outcomes. This is often accused of being a prescription, not a description. It tells you how to use the equations, but not what's happening behind the scenes. This gave rise to the infamous phrase, "Shut up and calculate." It's not a quote from Bohr, but it captures the mood. Stop worrying about metaphysics and just use the theory. It works. And the Copenhagen approach does work. It's the default interpretation in countless textbooks. It underpins semiconductors, lasers, and quantum computers. It has never failed a test. For many, that track record outweighs philosophical discomfort. But the discomfort lingers. If reality only becomes real when measured, what about the universe before observers? Most physicists say it doesn't require a conscious observer, just an interaction with a measuring device or the environment. But this leads to more questions. What counts as a measurement? Why does the universe follow this rule? The Copenhagen camp tends to shrug. The theory doesn't explain why collapse happens, just when. Competing interpretations like many worlds or objective collapse models aim for a more complete picture, but each has its own complications. Copenhagen, by contrast, is lean. It doesn't add hidden variables or multiply universes, it just lays out the rules. Maybe that's its appeal. In a field of strange possibilities, it offers a kind of calm. It's content to describe the world we can measure without claiming to know the machinery behind the curtain. Bohr understood this approach wasn't about making peace with reality, but with uncertainty. Quantum mechanics is weird. The Copenhagen interpretation invites us to accept that weirdness and work within it. It's not a final answer, but a quiet rule book. Imagine you flip a coin, it lands heads. But according to one interpretation, something else happened too. Somewhere, still real, the same coin landed tails. Every possible outcome unfolded, not as a probability, but as a real branch of reality. You just happened to be in the one that saw heads. This is the strange, elegant idea behind the many worlds interpretation. It began as an alternative to the wave function collapse problem. In 1957, Hugh Everett III proposed a radical idea. Maybe the wave function always evolves smoothly. Maybe when you measure a system, you don't force it to choose. Instead, the universe splits. Every possible outcome plays out, each in its own separate branch. It sounds like science fiction, but Everett was doing math. His version is mathematically identical to the standard one, just without the extra rule of collapse. In his view, the wave function never collapses, it only branches. Imagine an electron with spin up or down. Everett says no choosing is necessary. The measurement causes the system and observer to split. In one branch you see spin up, in the other spin down. Both outcomes are real. Both versions of you exist, each in a different branch. No randomness, just a growing, branching tree of reality. This doesn't rely on fantasy. Its appeal is that it sticks only to the mathematics we already use. It refuses to add the assumption that something magical happens when you look. The idea is weird, but the math is clean. Of course, if the universe is constantly branching, where do all these universes go? The theory doesn't say. The other branches are real, but they don't interact with ours. Once a split occurs, the branches decohere. They no longer interfere. They become invisible. This makes the theory hard to test, which is its central criticism. Supporters argue that's the wrong question. It's about not adding unnecessary assumptions. If the Schrödinger equation never includes collapse, why assume collapse exists? Occam's razor cuts both ways. Copenhagen keeps the universe small by adding collapse. Many worlds keeps the math simple by accepting a very large universe. Let's imagine the scale. Every time a quantum interaction has multiple outcomes, the universe branches. This isn't just in labs. It includes molecular collisions, radioactive decays, everything. The universe is branching constantly, exponentially. But we don't feel it, just as we don't feel the Earth spin. We simply see one outcome. It's also important that these aren't parallel lives in the sci-fi sense. You're not hopping between them or meeting your other selves. Each branch is causally isolated. This avoids the philosophical headaches of collapse. There's no need to define measurement. Measurement is just entanglement. But if every outcome happens, why does it feel like only one occurred? Many worlds redefines probability. It's not the chance something will happen, but a measure of how much you ends up in each branch. It's not intuitive, but neither is quantum mechanics. Despite its strangeness, many worlds has inspired serious research. Some believe it could help unify quantum mechanics with gravity or understand quantum computing. It also offers a unique perspective. No outcome is ever lost. Every possibility exists somewhere. The decisions you didn't make, the chances you didn't take, they're all playing out in parallel timelines. The universe may be more generous than we imagined, not a single story, but a vast library with every possibility inked into existence. Imagine pulling back the curtain on everything, the stars, the oceans, your hand. What if all of it, all matter and energy, wasn't made of solid things? What if the most fundamental stuff wasn't stuff at all, but vibrations, invisible ripples in fields that fill all of space? This is the profound world of quantum field theory, QFT, where the universe is built not from particles but from fields shimmering beneath everything. In classical physics, a field assigns a value to every point in space, like an electric field. Quantum mechanics says fields don't just sit quietly, they fluctuate, buzzing even when empty. Every field is quantum in nature. Even the vacuum isn't calm, it's restless. Here's the leap. In QFT, everything is a field. Every particle you've heard of, electrons, photons, quarks, is just a blip in its corresponding field. A particle isn't a tiny marble, it's a localized ripple, a wiggle in an underlying field that fills all of reality. Take the electron. Somewhere is the electron field, existing everywhere. When you see an electron, you're observing a specific quantized excitation of that field. The field got excited, and that's what you call an electron. Same for photons. The electromagnetic field fills all of space. A light particle is a ripple, a tiny vibration in that field. There's a field for every known particle. Quark fields, gluon fields, Higgs fields. So where did the particle go? In a sense, particles are a useful fiction, a way to describe how fields behave in discrete packets. The field is fundamental. The ripple is what we see. This shift in perspective is profound. It turns the universe from a set of blocks into a symphony, an orchestra of overlapping notes. QFT also explains puzzling features, like how particles are created and destroyed in high-energy reactions. They're just field excitations. Smash enough energy into a region, and you can jiggle a field hard enough to spawn a new ripple. That's how particle accelerators create new particles. Antiparticles? They're just another mode of excitation in the same field, with opposite properties. Forces themselves are mediated by fields. The electromagnetic force is charged particles exchanging photons. The strong force is gluons vibrating in the gluon field. Even empty space isn't empty. Fields are always jittering with vacuum fluctuations. These have measurable effects, like the Casimir effect, where two metal plates in a vacuum feel a force pulling them together, caused by changes in the field's energy between them. There's something serene about this picture. Space is an active participant, alive with potential. Every particle and interaction is just the field expressing itself. QFT is complicated, but the conceptual takeaway is elegant. Nature isn't made of things, it's made of excitations, patterns of energy. Even mass is an emergent feature. The Higgs field gives many particles their mass. Particles interact with this field like swimmers in molasses. The more resistance, the more mass. So here we are, nestled in a world of fields. You are a delicate pattern in the electron field, the quark field. Your thoughts are patterns of excitation. The atoms in your body are nodes in a cosmic meshwork of fields. You don't end at your skin. The fields defining you spill into the universe. QFT is the best map we have, where reality is an interwoven dance of fields, too subtle to ever fully catch. If the universe came with a cookbook, the standard model of particle physics would be its ingredient list, minus mystery spices like dark matter. It's a surprisingly compact recipe, elegant in organization and chaotic in naming. But this model is one of the most successful theories in history. It tells us what the universe is made of, how those parts interact, and why reality behaves as it does. At its heart, the Standard Model is a collection of elementary particles which, as far as we know, can't be broken down. Think of them as fundamental building blocks. There are three families: quarks, leptons, and bosons. Quarks are the stuff of protons and neutrons. There are 6 flavors: up, down, charm, strange, top, and bottom. Yes, those are their names. Physicists are precise with math, but chaotic with naming. The up and down quarks are the lightest and most common. A proton is 2 ups and 1 down. A neutron is 2 downs and 1 up. Everything you see is mostly up and down quarks plus electrons. The other quarks are heavier, rarer, and short-lived, like special guest stars. Next, the leptons. This group includes the electron, buzzing around atoms. Electrons also have heavier cousins, the muon and the tau. Like exotic quarks, these heavier leptons don't last long. Each charged lepton has a neutral partner, the neutrino. There are 3 of them, incredibly light, fast, and aloof. Neutrinos barely interact with matter. Billions pass through your body every second, unnoticed. So, we have 6 quarks and 6 leptons, 12 matter particles total. But matter alone doesn't make a universe. We need forces. That's where bosons come in. Bosons are the force carriers. Each fundamental force has its messenger particle. For the electromagnetic force, the carrier is the photon, the particle of light. It's massless, moves at light speed, and keeps electrons bound to atoms. The weak nuclear force, responsible for radioactive decay, has 3 heavy bosons: the W+, W-, and Z. They help turn neutrons into protons, fueling stars. The strong nuclear force, the glue holding quarks together, is carried by the gluon. Gluons are massless but energetic, constantly exchanging energy, and are responsible for why your atoms don't fall apart. Finally, the Higgs boson, confirmed in 2012. It's the manifestation of the Higgs field, which permeates space and gives mass to many other particles. Without the Higgs, most particles would be massless, unable to clump into atoms. To recap, 12 matter particles and 5 force-carrying bosons. This is the Standard Model, and it works beautifully. It has predicted outcomes with astonishing precision. It's not perfect, but it's stubbornly good. Of course, it has holes. It doesn't include gravity. The Standard Model is a quantum theory. Gravity is described by Einstein's general relativity, a classical theory. Merging them is a huge unsolved problem. Then there's dark matter. Observations suggest most matter is invisible. The Standard Model doesn't account for it. And dark energy, the force driving cosmic expansion, is also outside its jurisdiction. The Standard Model describes only about 5% of the universe. But what a 5% it is! Every atom, every interaction, every breath is contained within this lattice. The model is often called complete but unsatisfying, like finishing a puzzle only to see it's part of a larger picture. But what's there is stunning, hinting at a deeper unity. Theorists suspect a grand unified theory may one day unite them. So, what's the universe made of? Mostly quarks, a few leptons, and a handful of bosons. And don't forget the Higgs field. Without it, none of this would have any weight. At the intersection of complexity and perfection sits quantum electrodynamics, or QED. It's the crown jewel of physics, explaining how light and matter interact with such precision that even the pickiest decimal places are in awe. QED describes the quantum dance between electrons and photons. Every flicker of light, every spark, is choreographed by QED. It involves infinite interactions, yet its final answers match experiments with ridiculous accuracy, better than 1 part in a billion. How does it manage this? In the early 20th century, calculating these interactions was a nightmare. The equations blew up, spitting out infinities. Enter Richard Feynman. Along with Julian Schwinger and Sin Itiro Tomonaga, he found a way to make QED behave. Feynman made it visual. He invented Feynman diagrams, turning complicated calculations into childlike scribbles. In these diagrams, particles are lines. Time flows left to right. An electron might emit a photon and continue. That photon might hit another electron or loop back. Each path has a mathematical expression, and QED tells you to add them all up. Not just the most likely one, but every possible way the interaction could happen. This includes wild possibilities, like a photon becoming an electron-positron pair, which then annihilates into another photon. These are virtual particles, existing only in the math, but shaping the outcome. QED is like poetry written in calculus. It accounts for everything that could happen. When all possibilities are woven together, the result is a prediction so precise, it's stunning. One triumph is its explanation of the anomalous magnetic moment of the electron. The electron has a tiny magnetic field. QED calculates the quantum tweak to this field, matching experiments to over 10 decimal places. The theory also explains phenomena like Compton scattering, pair production, and radiation from slowing particles. All fall naturally from the QED framework. QED is the quantum field theory for electromagnetism, but it's also the prototype for others like quantum chromodynamics, strong force, and electroweak theory. Despite its mind-melting math, QED is intuitive. Feynman often said its rules could fit on a napkin. Particles take every possible path, each with a probability amplitude. You square the sum to find the actual probability. The rest is bookkeeping. This idea that nature explores every part is at the heart of the quantum worldview. An electron doesn't just go from A to B, it takes every route all at once. The universe calculates all possibilities, and QED is how we peek into that process. You might think a theory this strange has limits. You'd be right. QED doesn't include gravity or dark matter. But within its domain, it reigns supreme. It is the most accurately tested theory in science. Even Feynman, skeptical of admiration, admitted QED was extraordinary. But he also warned that nature always has more up her sleeve. For now, it's a masterpiece, a theory that began in tangled math and emerged as a clear, precise description of the quantum heartbeat of the universe. Light and matter interacting in an eternal whisper, described with such grace that even the decimals seem impressed. If classical computers are like efficient librarians, reading one page at a time, quantum computers are like strange poets who read all books at once in overlapping whispers and still find the answer. Quantum computing is real, built on the same bizarre quantum principles. To understand it, meet the qubit. A classical computer uses bits, either 0 or 1. A qubit, or quantum bit, doesn't just live in 0 or 1. Thanks to superposition, a qubit can be in a blend of both states at once. Imagine a spinning coin, neither heads nor tails until it's observed. A single qubit holds more than one state simultaneously. As you add qubits, the power grows exponentially. 2 qubits hold 4 combinations, 20 qubits over 1,000,000. A quantum computer could, in theory, explore an astronomical number of possibilities in parallel. That's the key: parallelism. It's not brute force guessing. It's shaping the probability landscape so the correct solution is the most likely to appear. It has another trick: entanglement. When qubits are entangled, their states are linked, even across distances. This allows for complex correlations that classical bits can't replicate. This entanglement lets quantum computers perform operations that would take classical machines vast amounts of time, like simulating molecules or factoring large numbers. But let's slow down. Quantum computers won't replace your laptop soon. They are specialized tools. Building them is hard. Qubits are incredibly delicate. They can be disrupted by tiny vibrations or temperature changes. Maintaining a qubit's coherence, its ability to stay in superposition, requires extreme care, often cooling systems to near absolute zero. Error correction is also tricky. You can't just copy a qubit state without disturbing it, the no-cloning theorem. Researchers invent clever schemes using many physical qubits to protect one logical qubit. Despite these challenges, progress is impressive. Labs have built computers with hundreds of qubits. Some have demonstrated quantum supremacy, performing tasks a classical computer would find impractical. Real-world applications are being explored. One is quantum chemistry. Simulating molecules is hard for classical computers, but quantum machines are naturally suited for it. This could revolutionize material science, drug discovery, and battery technology. Another area is optimization, like finding the best delivery routes. Quantum algorithms may find solutions faster. Then there's cryptography. Some quantum algorithms could one day break current encryption by factoring large numbers quickly. This has sparked post-quantum cryptography, designing encryption that even quantum computers can't crack. We're in the early days. Most quantum computers are noisy and fragile. The dream of a large-scale, fault-tolerant machine is still years away. But the journey is fascinating. Quantum computing takes the strangest parts of physics and turns them into tools. Superposition becomes a resource, entanglement becomes useful, even measurement becomes a step in the calculation. The very weirdness that made quantum theory unsettling is now being harnessed to solve impossible problems. It's like taming a wild wind by sailing with it. In quantum physics, we expect strange things. Particles tunnel, spin in 2 directions and entangle. But we usually don't expect quantum behavior in biology. Biology is messy, warm, and wet. A noisy world that should disrupt fragile quantum effects. Yet, life seems to be using quantum tricks. Take the robin. This migratory bird flies thousands of miles with uncanny precision. How does it know which way is north? Scientists suspected a built-in compass, but the details were elusive. Then came a radical idea: quantum entanglement. The hypothesis: inside a bird's eye, a protein cryptochrome contains a pair of entangled electrons. Light excites these electrons. Their entangled spins then interact with Earth's magnetic field, influencing a chemical reaction in a way that depends on the bird's direction. The idea was met with skepticism. Could entanglement survive in a living cell? Surprisingly, experiments suggest it might. There's growing evidence that birds really do rely on a quantum process to detect magnetic fields. If true, nature has figured out how to preserve quantum information in a biological setting. Now, let's look at plants. They are masters of a subtle quantum game, photosynthesis, turning sunlight into chemical energy. Light hits chlorophyll, and the energy is transferred to a reaction center. How does it get there so efficiently? It doesn't seem to hop randomly. Measurements suggest the energy explores multiple paths simultaneously, as if using quantum coherence to find the most efficient route. Imagine dropping a marble in a maze. Instead of rolling down one path, it spreads like a wave, feels every path, and settles on the shortest. That's how photosynthetic complexes might behave. This is astonishing in a warm, noisy system, yet quantum coherence seems to persist long enough to influence outcomes. Has evolution learned to harness quantum mechanics? Nature had billions of years to experiment. There's one more mystery: the sense of smell. We usually imagine smell works by shape, like a key in a lock. But that theory has holes. Molecules with similar shapes can smell different shapes can smell the same. An alternative is the vibrational theory. Our noses detect how molecules vibrate. The proposal is that when a molecule binds, electrons in the receptor might tunnel through it, and the likelihood of tunneling depends on the molecule's vibrational frequency. If true, your sense of smell involves quantum tunneling. Your nose might be sniffing both structurally and vibrationally. The idea is controversial, but experiments show that humans and fruit flies can sometimes distinguish molecules that differ only in vibrational frequency. Quantum biology is in its infancy, full of bold ideas and tentative experiments. But it's a reminder that the strange rules of physics don't stop at the lab. They reach into the feathers of birds and the leaves of trees. The same math that describes electrons in a vacuum also underpins a robin's chirp. Quantum effects are everywhere, woven into life itself. Perhaps as we understand these tricks, we'll gain a deeper appreciation for evolution's ingenuity. At the quantum level, particles blur into superpositions and occupy multiple possibilities. It's the playground of probability, not certainty. Yet, when you look around, you don't see a shimmering world of maybes. You see a coffee mug, a desk, a cat, hopefully alive or dead, but not both. You interact with a world that feels solid and predictable. Why? The answer lies in decoherence, a quiet but powerful process. It's the mechanism that explains how the quantum world loses its quantumness and becomes the classical world we know. Imagine a single electron in an isolated superposition, a spread of possibilities. Now, back on Earth, things aren't so quiet. There's air, heat, photons, vibrations. The moment your quantum object interacts with any of this, it begins to lose its quantum coherence. The neat interference patterns blur. This is decoherence. It's not that the superposition disappears, it's still there, but the quantum system becomes entangled with the environment. All those particles it touches become part of its description. When that happens, the system stops behaving like an isolated wave and starts behaving like something ordinary and predictable. Quantum systems want privacy. The moment the environment peeks in, they lose it. Nature itself is always watching. Air molecules and photons act like tiny, constant observers. They don't collapse the wave function, but they smear out its coherence, making interference impossible. Decoherence is a gentle erosion, not a violent snap. It just needs time and contact, and it happens incredibly fast. For microscopic objects, you can isolate them. But for macroscopic objects, things you can touch, decoherence happens almost instantly. The more massive the system, the faster its quantum weirdness dissolves. That's why you don't find your shoes in a quantum blur. Interaction with the world has pinned them down. Decoherence doesn't destroy superpositions, it hides them. They become entangled with so many environmental variables that you can't access them. They become effectively classical, even though deep down everything remains quantum. This helps explain how we get from probabilities to outcomes. Decoherence doesn't solve this completely, it doesn't pick which outcome occurs. But it explains why we don't see quantum interference in large systems. It creates the illusion of collapse by bleeding quantum information into the environment. The wave function is still there, but it no longer behaves coherently. This gives us a bridge between the quantum and classical worlds. Classical physics is still useful for building bridges, but beneath it, the universe hums with quantum rhythms. Decoherence gently veils that underlying weirdness. Picture walking on a frozen lake. Beneath is fluid, quantum water. The ice is solid. Decoherence is what freezes the surface. It doesn't eliminate the water, just keeps it out of reach. This has practical consequences. Quantum computers must fight decoherence constantly. Their qubits are delicate. A stray vibration can collapse their quantum behavior. That's why they're kept in ultra-cold, isolated environments. Decoherence also plays a role in interpretation. Some theories suggest there's no need for collapse. Instead, decoherence explains why outcomes appear definite as the alternatives become unobservable. Decoherence doesn't solve every mystery. It doesn't answer why a measurement yields a particular result or if the wave function is real. But it explains why quantum weirdness fades into classical certainty in daily life. It shows the world we see is shaped by the quantum realm, filtered through continuous interaction. So, thank decoherence that your mug behaves as you expect, taking a universe of maybes and presenting it as a firm handshake. Imagine an experiment so strange that the act of deciding when to observe seems to reach back in time and affect what happened earlier. This is what happens in the delayed choice experiment and the quantum eraser. If you hoped quantum physics was starting to make sense, this is where time itself starts to shrug. Let's start with the double slit experiment. Fire particles at two slits. If you don't observe which slit they go through, they create an interference pattern, acting like waves. If you place a detector to find out which slit, the interference disappears. The particles act like bullets. Knowing the path kills the wave behavior. Now, in the delayed choice experiment proposed by John Archibald Wheeler, you set up without measuring the path, but you reserve the right to decide after the particle has passed the slits. Here's where it gets surreal. The pattern on the screen will match whatever choice you make, even if that choice comes after the particle supposedly decided how to behave. It's as though the particle knows your future choice and adjusts its past. The delayed choice experiment suggests the quantum world doesn't commit to a reality until forced to, not just in space, but in time. The act of observation might determine the history. Then, physicists created the quantum eraser. In this setup, you mark the particles so you could know their path, but then you use a trick to erase that information after they've been detected. When you erase the which path, the info, the interference pattern comes back. The particles behave like waves again, retroactively. This raises an unsettling idea. Reality might not be finalized until all information is settled, not just at detection, but when we decide what to do with that information. It's like Schrödinger's cat stretched across time. Whether the cat was alive or dead depends on a decision made after as you open the box. What's going on? One interpretation is that information, not matter, is the true currency. Outcomes aren't locked in until you ask answerable questions. This doesn't mean time travel is real or that we can change the past. It suggests our usual picture of time as a one-way street might not apply at the quantum level. Events are part of a strange, holistic web where outcomes emerge only when the entire system is considered. There are limits. These experiments don't allow communication with the past. The results always obey causality at the large scale, but they hint that under the surface the rules are flexible. Some physicists describe it as entanglement and correlation, not causation. The particle doesn't know your future. The experiment's final setup just defines what patterns are visible. Others lean into a block universe interpretation where all moments exist simultaneously. Your choice was always part of the timeless story. And others just shrug and say, "Shut up and calculate." The important thing is, the universe is under no obligation to conform to our common sense. Our intuitions are built for macroscopic objects. Down in the quantum mist, the rules are subtler, less linear, and much stranger. These experiments don't break physics, they reveal the richness beneath it. If you zoom far into the heart of the universe, you'd find a world where certainty slips away. A world where outcomes are described by probabilities, where particles don't have positions until you look, and even then, they're just a cosmic dice roll. Welcome to the quantum universe, a place that's not just small, it's uncertain. Quantum physics suggests that randomness may rule. This idea made Albert Einstein uneasy. He once declared, "God does not play dice with the universe." In classical physics, if you know the position and velocity of every particle, you can predict the future with precision. It's a neat, deterministic framework. Quantum mechanics breaks that chain. It replaces precise predictions with wave functions, mathematical objects describing all possible outcomes. When you make a measurement, the wave function collapses into one of those outcomes. But which one isn't determined ahead of time? It's genuinely random. It's not a result of human error or missing information. It's baked into the structure of reality. The best you can do is calculate the probability. Some interpretations, like many worlds, dodge this by suggesting every outcome does happen, just in a separate branching universe. When you measure spin up, another version of you sees spin down. No randomness, just infinite outcomes. But from your point of view, the experience is just as unpredictable. This raises deep philosophical questions about cause and effect, free will, and the laws of nature. It's unsettling, the idea that the universe is improvising. Yet, randomness isn't chaos. Quantum mechanics is astonishingly precise in its predictions. It says, here's a list of what can happen and the odds. When physicists test quantum predictions, they find agreement with experiments to 12 decimal places. So, even if outcomes are random, the structure of that randomness is deeply orderly. It's like rolling 100 dice and finding they always sum to a predictable average. The behavior of large numbers of particles becomes reliable, giving rise to classical physics. This is why your coffee mug doesn't tunnel through the table. In this sense, randomness is a feature, not a bug. It adds flexibility, it allows for novelty. It might be essential for life and creativity. Think about mutation in evolution. If every event was determined, there'd be no variation. Throw in a little randomness, and suddenly the universe has options. Some take comfort in this. A deterministic universe feels like a clockwork prison. A probabilistic universe is one where the unexpected can happen. Of course, randomness also comes with mystery. When we observe one state, why that one? Quantum mechanics doesn't offer a reason, just the odds. It's like flipping a coin and getting heads. It just had a 50% chance. This suggests the universe is not fully knowable in the classical sense. There's a ceiling to certainty, yet we can thrive in that uncertainty. Quantum randomness also ensures no two things are identical. This tiny unpredictability keeps the universe alive and interesting. So perhaps the universe does play dice, not recklessly, but with an elegance so refined it creates galaxies, atoms, and thoughts. We can appreciate it, not as a flaw, but as the soft hum of possibility. If quantum physics were merely a set of equations, it would be one of humanity's greatest achievements. But it's special because it doesn't just describe particles, it invites us to reflect on what it means to know and to be. In peeling back the layers, quantum physics doesn't just reveal new answers, it reshapes the questions. We tend to think of reality as solid, fixed, out there. The quantum world disagrees. It suggests that at the smallest scales, reality isn't fixed. It's a set of possibilities, like dreams waiting for an observer to nudge them into form. A particle in superposition isn't just undecided, it's all possible states at once. When we measure it, it settles on one outcome, as though the universe softly exhaled and chose a story. This raises a quiet thought. If observation shapes outcomes, are we as separate from the universe as we believed? Or are we, as observers, part of the grand entangled dance? For physicists, these are technical questions. For us, they feel almost spiritual. But quantum physics isn't here to offer easy answers or metaphors for self-help books. Yet, it leaves us with something precious: humility. It reminds us that our everyday intuitions about space, time, and cause are not the final word. The familiar world is just one version of reality, filtered by evolution, shaped by our senses. Quantum mechanics becomes a mirror, showing us the edges of our knowledge and the breathtaking strangeness of our home. Think of Schrödinger's cat, not as a literal paradox, but as a metaphor for how we live in uncertainty, juggling conflicting possibilities. Whether waiting for a test result or wondering if it will rain, we exist in a quantum state of our own, hope and fear, layered gently until time or choice collapses the wave. Maybe that's the secret beauty. It's not telling us the world is unknowable, just that it's not obligated to be obvious. There's a softness to that, a quiet freedom. If certainty isn't guaranteed, neither is limitation. If the world isn't pinned down until observed, then possibility is always alive. Even the word quantum has poetry. It comes from the Latin quantus, how much. It points toward boundaries, discrete packets, the smallest allowed unit of change. Maybe there's meaning in that too. Even in the swirling confusion, there are limits, minimum steps. Not everything is continuous, some things change in leaps. When you dream, you leap into worlds that don't exist until they do. When you wake, you carry back the feeling of possibility. Quantum physics feels like that, like waking and realizing the world is weirder and more wonderful than you guessed. This can be unsettling. We like cause and effect. We like knowing. But maybe certainty is overrated. Maybe it's okay to live with questions that don't have answers, to wander in a forest of probabilities. Maybe that's where wonder lives. Physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He meant it. Even those who work with the math admit it's not something you get in the usual way. It's something you accept, like a poem. It works, it's precise, it's testable, yet it refuses to be pinned down by ordinary logic. Maybe that makes it more honest. The universe was never obliged to be simple. It just had to be. So, as we drift through quantum thought, maybe the most important lesson isn't about particles, but about perspective. To see uncertainty not as a flaw, but as a feature. To let go of the need to know everything and rest in the beautiful truth that we are part of a cosmos still unfolding, still shimmering with possibility. Thank you for listening. Whether you're still awake, drifting gently, or halfway through a dream, we've wandered a long way tonight through slits in cardboard, thought experiments with cats, and rippling fields. We've met particles that behave like waves and forces that play by rules we're just learning to translate. Somewhere, we began to see not just the oddness, but the quiet beauty. At first, it might seem too strange. A universe where something isn't real until observed, where cause and effect get blurry. But quantum physics gently reminds us that the world we know is only the surface. Beneath it lies a softer world. Stranger, yes, but more flexible. A world built not on certainty, but on shimmering possibility. And we are part of that world. We are made from these same quantum fields. The atoms in your fingertips, the light in your eyes, the oxygen in your lungs, all obey the same uncertain laws. You are not just in the universe, you are Sophit. Doesn't that feel poetic? Back at the start, I asked where you're listening from. Maybe you're curled up in bed or gazing at the ceiling. Wherever you are, I hope you found something in this journey, something soft, strange, or simply still. Remember that when we stare into the heart of matter and ask, what is real? Quantum physics doesn't offer a final answer. It offers a mirror, a shifting one. A reminder that knowing deeply doesn't always mean understanding completely. That questions can be as beautiful as answers. That mystery is not a failure, but a feature. It's tempting to wish for more clarity. But maybe in this tangled uncertainty, there's a different comfort, a gentle truth that you don't need all the answers to feel at home here. Even if the particles are uncertain, the moment you're in is real. The breath you just took, the thought that drifted by, the weight of your body sinking into stillness. That's quantum too, and it's enough. So, thank you for giving your time and quiet curiosity to this exploration, for trusting the strangeness and sitting with the not knowing. And if you've already fallen asleep, wonderful. The quantum world will still be here when you wake. From the Sleepy Scholar, good night.